So hi everybody and welcome to this fifth video in the solutions unit series. So here we'll be discussing about the thermodynamics of ideal solutions of liquid in liquid. Liquid in liquid. Okay. So first of all, let me reiterate what is an ideal solution. A solution is said to be ideal if its constituents follow Raoult's law under all conditions of composition. That is the partial pressure of each and every constituent. Constituent is given by given by so where your Pi is the partial pressure of constituent I and Xi is the amount fraction and your Pi star is the corresponding vapor pressure of the pure constituent. Okay, so now what are the thermodynamics of ideal solution? So we know that mu I solution, we have already derived this, is given by mu I L plus RT ln Xi. This has been derived in the previous video. Okay, so where mu I is the chemical potential of ith constituent and mu I star is that of the pure chemical potential of the pure liquid of constituent I, and Xi is the amount fraction of the constituent in the solution. Now the changes in the thermodynamic functions when ideal solution is formed by mixing pure components can be readily calculated as described below. First we will calculate the change in Gibbs free energy. Okay, so what do we have change in Gibbs free energy? Delta mix G will be equal to G final minus G initial. So what is G final? G final is your Ni into, see what is mu? Mu is molar Gibbs free energy. So therefore G will become what? N into M, that is for one component. Now for multiple components what will become? G will become Ni suppose there are two constants Na mu A plus Nb mu B. So if there are n number of constants, G will become the summation of Ni mu I, right? So that is what has been given here. So mu I of solution, okay, ith constant in the solution, minus I Ni mu I star in its pure state liquid. Okay, so let us if I take the Ni I mu I solution minus mu I star liquid. So by making use of the previous thing of how we have shown that mu I of solution is like uh, as has been mentioned before. So this is mu I star of liquid. Let me go back to that equation, plus RT ln x minus mu I. Now what will happen? Mu I will get cancelled. Now what you are left with is Ni RT ln xi. So I can again rewrite this as n total into Ni divided by n total RT ln xi, which I can rewrite it as n total I. What is this? This is xi RT ln xi. So your delta G mixture, sorry, there is a way to write this. Delta mix is given by this, where n total is the total amount of all the constants present in the solution. Solution. Okay, so let us copy this particular tick. This is all we need for next copy. Okay, now we know that delta mix G we know. So what is the change in entropy on mixing? So we'll go to the next thermodynamic function. Entropy on mixing. So we know that dG is equal to VdP minus SdT. Right. Now at constant pressure, dP becomes 0 and dou G by dou T at constant pressure and holding all other amount of all the constants to be constant, what you get is minus Z. You can check this out. So you can just differentiate this particular thing and find. So because G and S are state functions, you can write that delta mix. You can even calculate for the changes provided your pressure and Nj's is equal to minus delta mix of entropy, not just entropy. Mix entropy. Now if I substitute for delta mix G from here, from this particular equation, what do I get? My delta mix entropy is given by minus of dou n total RT I xi ln xi, right, divided by dt, holding pressure and amounts constant. So if you differentiate that with respect, what you will end up getting is minus n total into r. So only thing is this t will get cancelled. Xi ln xi. So this is your change in entropy on mixing. Let us go to change in enthalpy on mixing. So we know that delta mix G is equal to delta mix H minus T delta mix S, right. So your delta mix H will be equal to delta mix G plus T into delta mixing of S. So now if you substitute values for delta mixing of G and delta mixing of S from above, you will end up getting delta mix H as 0. You can do that. So this is, so thus in the formation of ideal solution, you can substitute. Neither heating nor cooling is observed. Okay, the last thing, change in volume on mixing. So same thing, dg is equal to v dp minus s dt at constant temperature. dt becomes 0 and therefore your dg by dp at constant temperature and holding uh, amounts of all other constants constant, you get your delta, you get your v. You can do that. Okay, so from this equation you can get here, and since g and v are both state functions, this can be extrapolated to mixtures. Now you can substitute for delta G mixture from above. Since delta G mixture does not have any P, has no mention of P, so what will happen is Ni n total RT xi ln xi by dou P, and this being at constant temperature and not pressure in this. So since there is no P here, so this will give you 0. So that was about your thermodynamics of solutions. Thank you.